guys, how you doing? My name is Kelly Cox. I want to just go over the proofs that I've done for prime numbers and for the Riemann Zeta function. Right, I was reading this book, saw the $1 million prize that got me interested in looking at this a week ago, and right over the last week I've gathered some information that I can't find anybody talking about on YouTube. So I'm going to go through the basics as I see them real quick. Right, you don't need a number higher than 7 to understand the patterns built in the prime numbers. Right, this includes 1 because it's the start of all your patterns. You can include it, exclude it from your formulas, but you can't exclude it from any pattern. So 1, 2, 3 is your first and only consecutive primes. 2 times 2 eliminates this from happening again. 3, 5, 7 is your first and only triplets. And again, the next prime eliminates that. 3 times 3. 2 times 3 creates the twins. Right? 2 times 3 plus or minus 1 gives you all the rest of your primes are based on that. Right, so we know where all the other primes can be. Right, they're going to be the twins. If we apply the correct patterns, we can rather quickly determine where we're going to see the next set of twins, the next prime. Right, and so there's 2 patterns. Right, your basic patterns are created prime times the next prime times the next prime times the next prime. Right, this is our basic pattern, and then you have your elimination pattern, which is prime squared. Right, so these work together, but you can't put them together. Right, they're 2 different patterns doing 2 different things, but working together. Right, so here are the basic patterns. The first one is 1 times 2. It repeats to infinity. Right, eliminating all even numbers. Right, the next one is 1 times 2 times 3. Repeats. Right, the first pattern repeats 3 times, and this pattern creates the twin pattern. Right, the next one is 1 times 2 times 3 times 5, repeats 5 times. Right, and 1 times 2 times 3 times 5 times 7. Right, the third pattern repeats 7 times in this pattern. It gets you to 210. Right, the twin patterns is in. You take any number, 2 times 3 builds the pattern. Right. Now, when I say elimination, right, we're going to eliminate primes at prime times prime. Right, so 5 times 5 eliminates 25, which is the first twin to lose. Right, that's the first number that we lose from the twins. Right, and so the formula is prime times prime minus 1 divided by 6 gives you a number divisible by 6. Right, so I can turn around, take that number times 6 plus 1, and it will be the prime, right? I've seen a lot of videos showing this exact formula, right? But it's always the prime plus, right, a number plus 1 from the multiple of 6. So what I haven't seen is the next time that prime is used, prime times the next prime, eliminates the number from the lower side. Alright, so prime times the next prime plus 1 divided by 6 equals the value divisible by 6. And I can take that number times 6 and subtract 1 and be back at the prime. That I haven't heard talked about. After the initial 2, right, you're going to have that prime eliminating, right, the same location, right, so prime times prime divided by 6, add the prime number, gives you the next high prime or high side twin that it's going to eliminate, right? So 5 times 5 divided by 6 is 4, plus 5 gives you 9, times 6 is 54, so 55 would be the next prime eliminated by 5. Right, and then I can do the same calculation for the low twin. And so this is going to continue to infinity, right? No other prime can eliminate what these are, right? The initial 2 primes, right? So a prime squared is never going to be eliminated any other way, right? That prime is going to start a pattern. Right, so I want to go back to our patterns, right, of just how the primes get set up, right? So 1 times 2 is our original pattern. This is what it looks like visually if you're looking at 2 numbers, yellow being all the primes divisible by 2. The left side would be pattern numbers divisible or just odd numbers, right? Even on the right, odd numbers on the left. 9 is the black spot, so it's not part of this pattern. So just looking at this pattern, right, no even number is going to be a prime, right? All of our potential primes are 3 and then every odd number after that. Our next pattern is 1 times 2 times 3. This is the most important pattern, right? As you can see visually, you're only going to have primes showing up in the 1 and 5 column. So if I cycle this every 6, start the pattern over, you see there's nothing changing about the pattern until I get to 5 times 5 and I start losing primes, right? But just looking at this pattern, right, 25 is still a potential prime, right? Because I haven't looked at my next pattern. I need the next prime to know 25 is not a prime, right? If I look at this pattern, 1 times 2 times 3 times 5, right? This is what it looks like, and you can see there's only 2 columns out of 30 that are being eliminated by this new prime. Right, and there are 5 and 25, 35, 55, 75, no, 95. And 85. Right, and we also have 7 getting into the mix and killing off a couple of primes. Right, and so this is what it looks like, right, when I look at it in the rows. And you'll see at 30, right, 1 times 2 times 3 times 5 is where all of these primes are going to converge, right? The next convergent is 210 when we multiply it by the next pattern, 7. Right. So these are your cycle patterns, right? Which, you know, prove, right, that there's never going to be another even pattern. That every prime is going to be plus or minus a division of 6, right? Plus or minus 1. You know, 2 times 3 plus or minus 1, right? That's going to be the only way to find a prime. After that, right, the rest of the patterns just show you how often, right, we're resetting our patterns. Right, so now we'll look at the twin patterns. Right, you can see here, right, I have all the multiples of 6 up to 90, and you can see how, right, 5 times 5 is 25, 5 times 7 is 35, 5 times 11 is 55, 65, 85, 95, right, so that pattern is unchangeable. There's nothing, right, it's going to go to infinity, eliminating 2 primes out of every 10, right? You're not going to change that with 5. Now when you add 7, right, you're going to eliminate 2 out of every 7 sets of twins. Right, so 1/7 of 14 numbers is going to be eliminated by this. Now, here we start complicating things because 35 is eliminated by both those numbers, right? So now I have to take into account which prime, my lowest, is eliminating a prime. So you're going to be highly accurate with 5, and as you get farther away from 5, you have to account for more duplicates. And I'll show you a formula that you can use, but you'll have to account for these duplicates. But what I want to show you is the formula for just doing simple math. Again, the only primes we're concerned with are the ones with the lowest value in prime times the next prime greater than 3. Right? So you can take any random number, square it. This gives you the highest prime that's going to be able to eliminate from that number. Right? So then I'm going to take that set of primes and take my number divided by that prime, and it's give me the highest multiple of that prime that I can use to eliminate the twin primes. Then I'm going to calculate the total twins that I can have, or the total primes from the twins. So I'm going to take the random number divided by 6 if it's a low prime, right? So if the number comes up to a random number 0.8, we're going to round up. Any other, if it's position 5, we want to round up. If it's any other position, 1, 2, 3, 4, 6, we're going to round down. Right, so that we have the right amount of twins that we're dealing with. So if our random number is 25, right, I'm going to square 25, I get 5. 25 divided by 5 is 5, so 5 times 5 is my only elimination, right? My twins are going to be 25 divided by 6 is 4. I'm going to round down to an even 4 times 2. It gives me, there's 8 total primes in that we're looking at in the number 25. Alright, potentially I can only have 8 primes. Alright, so this result gives me 1 to eliminate from the twins. So twin primes minus 1 is 7. So my total primes is 20. In 25 is 7 plus my twin builders 2 and 3. So I have a total of 9 primes in the number 25. Right? I don't have to worry about any of the 3s or 2 multiples. Right? Those are the builders of the twins, so they're never going to eliminate anything. Right? And so if we look at 50, my square number is 7, so 5 and 7 are going to eliminate numbers total of 8 multiples of 6, giving me 16 total primes. I'm going to subtract 3, that's 13, add 2 and 3, gives me a total of 15. 125, 11 is going to be my highest prime, and then, right, 125 divided by 5 is 25, so I get 8 primes that I'm killing with 5, 4 with 7, 1 with 11. I have 20.8, right? So I'm in the 5th position. So I'm going to add, round the number up to 21, gives me 42. Minus 13 is 29, add the 2 and 3 is 31. 175, right, I've added the number 13, 29 twin primes, so that gives me 58. I'm going to subtract 20, which leaves me with 38, so a total of 40 primes. And then one more, 200, 13 is still my highest prime, because 14 is not. 33 total twin sets, so 66, minus 22 is 44, total 46. Alright, so basically I'm just showing you the logic that goes into how you would build your formula. Closing thoughts. Right, there's a pattern that gets talked about, but I just want to show it real quick. There's the twos, so these are patterns that are happening. With what I'm looking at, I don't see them adding anything yet, but here's the threes. At these stages, right, this is 3 times 9 is 27. 9 times 9 is 81. Don't really see, right, they're just patterns that I see developing, but I'm not using them or have a need to make my calculation. And then a couple other patterns, right? This is the first triplet prime. 5, 7, 11, 13, 17, 19. You can't have that again because 5 times 5 eliminates that from happening again. And then the next patterns, 7 times 7 eliminates this pattern from happening. I haven't been able to find the 11 times 11 pattern, but as you can see, right, it's probably going to be probably 30, 40, 50, 60 numbers in that next pattern, so it's just hard to see visually in a small amount of space. Just real quick, I want to show you how quick we get in, right, the patterns in the millions at the 19th prime. And with the 10th, right, we're only looking at 10 primes, right, and this is including 1, 2, 3, right, as part of this, right, so we're at 6.5 billion at just the first 10 primes, right, and you have the pattern above it going, cycling through this pattern 223 million times, right, so it's repeating that amount of time. So you can quickly see, right, it's not going to take much to be near infinity really quick. So not really going to see many pattern changes after this, right, at 10 primes. Right, there's a lot of patterns there. And then, right, I decided to, right, out of every n twin primes, divided by prime divided by 2 prime. Alright, so 1/5 of, right, if I look at 5, right, I have to look at 5 sets of twins, and in those 5 sets of twins, 1/5 of those prime numbers are going to be eliminated. Right, so 2 out of every 10, right, and then it's every 7 twins, once the number 7 prime is going to eliminate 1/7 of those. So 2 out of every 14 numbers. 11, you're going to have to look at 11 twins. You're going to eliminate 20 or 2 out of every 22 sets of numbers. And so on. Alright, so you can see your pattern for finding them. Right, I built this thing to look at the first 1,000. Right, you have a total of 332 primes before you start eliminating them. Right, and so just the raw numbers are going to put you at, it's going to say 234 primes are eliminated. The problem with that is it's not looking for duplicates. So you are eliminating 234 primes, but 5 times 7 is 2 of those. Right, so we're not going to eliminate 5 times 7 twice. So I took those, right, the S2 is accounting, well, S1 accounts for 5, 7, 11, 13 itself. So I'm subtracting 1 from each number. And then for S2, I'm accounting for 5 times 7, 5 times 11, 5 times 13, so I'm subtracting the ones that I can quickly calculate in my head, and I'm at 85% accuracy. Right, so what I'm not accounting for is the number 175. Right, it's 5 times 7. Right, so again, it's I need to go through and find those type of patterns that are duplicates. Right, so I need to go through my stages and look for patterns that are duplicates, that are being counted multiple times. Right, but real quick, I got a number that's, right, 85% accurate. 198, the real number is 169. And then the last thing I want to go over is the Riemann Zeta proof that I'm working on. So the thought process I went through was, how can I remove all primes? And what I mean is, I want to take the number 2, multiply it times every number, and it give me every number from infinity to negative infinity, right? And so if I can do this, my thought was, I'll show where the zeros are on the 1/2 line. Right, so here's the formula pattern I came up with. 2 times 0 is 0. 2 times 0 plus 2 times 1/2 is going to give me a 1. 2 times 1 is 2. 2 times 1 plus my function gives me 3. So my function's giving me odd numbers based on a half. My even numbers, 2 times an odd number or an even number, right, it's going to give me an even number. I move that to the complex plane, that's going to put me at 0, right? It's going to give me a value of 0 in that plane. And that's what the odd numbers, since I'm using a half, it's going to give, it should give me a number in the plus I and minus I. This is where I'm trying to get to. So this is the, right, I still haven't seen anything on this that is of use to me to see the pattern. There was like a 2-second clip that showed some of the zeros on the 1/2 line. Right. So I want to work on this, but somebody's going to have to tell me what to work on if this doesn't help. That's all I got. I'll talk to you later.